This is an introduction to Laplace transforms. We're going to use Laplace transforms to be able to solve ordinary differential equations, linear ODEs, and we're just going to go through a couple examples in terms of building transfer functions. We can use you do frequency response analysis, control system design, stability analysis with Laplace transforms. So the main reason why we want to use Laplace transforms is because we might have, for example, a differential equation. Okay, and Laplace transforms help us to get it into algebraic form, where we can rearrange and analyze it, and then as a final step we can also bring it back into the time domain. Okay, into the time domain and get an explicit solution for that expression. Okay, so this is the definition of a Laplace transform. Okay, so if you have a function f of t and you want to be able to convert it to the Laplace domain or the S domain, what you do is you integrate that function, you multiply it by e to the negative st, you integrate it with respect to time, and you integrate from 0 to infinity. Okay, so f, and we use capital symbols for the Laplace domain typically, and lowercase for the time domain. And notice this L operator is the one where we have take the Laplace of a function, and then that is going to be equal to that function in the Laplace domain. Okay, so we can also do the inverse Laplace. Okay, so if we have L inverse of a variable or a function, okay, so it could be y of s, for example, that's going to be y of t. And also they're linear operators. Okay, so if I have x and y, those are two functions, I can have the a constant come out front and also divide and take the Laplace of those terms individually. Okay, so this is the Laplace of a times x of t plus b times y of t in the Laplace domain. Okay, so also it works the other way, the inverse Laplace, you can go back the other way. These are linear operators. Okay, so let's just visit this first one. Actually, I have a worksheet here that you can also download from the course website. Okay, so let's just go to that worksheet, the Laplace worksheet, and let's just go ahead and use this. If you want to go to the course website, just go to APMonitor.com and then visit the process control course, and if you go to schedule, okay, so let's go down on the lectures, and we're actually going to be posting this to Laplace transforms, and this is the lecture 16 handout. Okay, so I'm just going to use this in Word just so I can write on it. Okay, so let me go ahead and just start up. Okay, and so we're just going to do a constant a. Okay, so we want to do the Laplace of a. And so that is going to, we just plug it into a right here for f of t. And then let's go ahead and just integrate this. So we are going to have negative 1 over s times a e to the negative st, and that is going to be from 0 to infinity. Okay, so if I plug in infinity here for my t variable, then this term is going to go to 0. And then if I plug in 0 into this expression, then this term is going to go to 1. And so that's going to be negative a over s, and so that's going to be a over s. Okay, so that's the Laplace of a is going to be a over s. And that's also the step function as well. Okay, so let's do a derivative of a variable or a function, and just to give you a little bit of help on this, we're going to want to use integration by parts on this one. And I always forget the integration by parts, so I always start with a chain rule, and then I just rearrange and rearrange into integration by parts. But essentially, this is going to be our dv dt, and this part is going to be our u. Okay, and so when I write this out, okay, so that's going to be equal to f of t times e to the negative st, and we're going to integrate from 0 to infinity, and then I have minus, and then I have v. Okay, so I'm going to integrate from 0 to infinity, and then I have f of t, and then du dt. Okay, so that one is going to be times negative s times e to the negative st dt. I'm going to go ahead and bring that out front. Okay, and okay, so let me just go ahead and evaluate this from 0 to infinity. If I plug in infinity, again, this term is going to become 0. And if I plug in 0, that's going to become 1. So I'm going to have negative f of 0. And then I had my plus s, and 0 to infinity f of t times e to negative st dt. Now, lo and behold, that is actually our definition of the Laplace transform. Okay, so if we come up here, you'll see that that is our definition, and that is just going to be equal to f of s. Okay, so that's going to be s times f of s minus f of 0. That's our initial condition. Okay, so if we use deviation variables, that's often going to go to 0. So the Laplace of the derivative of a function or variable is going to be s times the Laplace variable. Okay, so that is those are just two examples of deriving this, and we don't necessarily want to integrate these all the time, or sometimes they're difficult to remember. So we do have some tables, some Laplace tables. So this is time domain, and this is Laplace domain, and so we can go back and forth. Okay, so a couple of them that are common are going to be 2, 3. We're going to use these commonly in this class. 13, and this is table 3.1 on page 42, 43 of your process dynamics and control. Okay, you can also use MathCAD. So if you plug this in and just select transform and Laplace or inverse Laplace transform, it'll do the Laplace transform for you. Okay, so there are a number of good computational tools for that as well. Okay, so that's all I wanted to cover on this one. Let's go back here. Okay, so we derived this one for the constant. Okay, now I want to also talk about a step function. You'll see that in, for example, in your table, you'll have a step function that's number 2, and then also number 26. You'll see that. That's just as simply if you're below time. Okay, time equals 0. That's going to equal 0. And above time 0, that's going to equal 1. Okay, so if I have s of 5, that's going to equal 1. If I have s of negative 2, that's going to equal 0. Okay, so if I plot that, here's my time equals 0, and I went from 0 to 1. Okay, so those were all the points, and then at time 0, it turns into 1. Okay, now if I also have a step of t minus 5, okay, then that just time shifts it. Okay, so here's time equals 0, and then I just have my step that occurs at time 5 up to a value of 1. Okay, so that's a step function, and here is the, it's just 1 over s. Now if I have a time delay like this, then what I'm going to do is just multiply by e to the minus 5s. Okay, in the Laplace domain, if I have t minus 5 step that's delayed, I'll just multiply by e to the minus 5s. Okay, so we covered the derivative one as well, just with that worksheet. Here's some higher order derivatives. Okay, so just keep in mind this one. You have, first derivative. You'll have nth order derivatives here. Just for higher order derivatives of a function. Okay, I'm just going to skip that. You also have, for example, exponential functions, rectangular pulse functions. Okay, this is just a combination for example, if you have something like this, okay, you can really think of that as a step up, and then after a little bit of time, you're also going to have a step down, and you're just going to add those two together to get your rectangular poles. Okay, so this might be, for example, 1 over s, and this one might be 1 over s e to the negative theta ps. Okay, so this is your delay right there, your delayed step. I'll put negative there for the negative step. Okay, so that's going to be 1 over s times 1 minus e to the negative theta ps. Okay, so that's going to give us a rectangular pulse. So you can combine these functions in the Laplace domain to get more exotic functions, but get those from the basic functions. Okay, and there we had the rectangular pulse. Okay, we also have an impulse function. So this is actually a signal that at the time when it starts, it's it's going to go up to infinity, and beyond. Okay, so but the area under this, the area is going to be equal to 1. So if you integrated this, the area would be equal to 1, but it goes to infinity. It's kind of a hypothetical signal. But anyway, the Laplace of that Dirac delta function is equal to 1. Okay, as I mentioned, there are going to be some tables that we're going to use, and those will help get us back and forth between the time and the Laplace domain. Okay, so here's some other ones. We're going to, these other ones that I mentioned, 26, 24, we're going to use that one a lot. If I go back here, we're going to use a step, ramp. There's just a couple that we tend to use more than others. Okay, and also for, let's see, second order systems, we might use 9, and actually these, okay, yeah, so these we're going to use 21 as well. Okay, so these are some of the more commonly used ones that we'll use in this class. Okay, so we can practice, this is a step function, okay, it goes from 0 to 1,000, okay, and that's just going to be the step, and that's just going to be 1,000 divided by s. Okay, so if we go back to our tables, we found it right here as number 2. Okay, and then you can just look these up as well. Okay, so 5 e to the negative 6t. Okay, go back to your Laplace tables. Okay, and you'll go ahead and use that one to bring it back over to that form in the Laplace domain. And then sine wave, I think we had sine in there as well, and then we'll use that one from our Laplace tables. Okay, so you can convert each of these and then have an expression for the Laplace. And also higher order derivatives, you're going to need some derivative values at time equals 0, just your initial conditions, in order to be able to derive the Laplace transform of that. Okay, so here are the answers to each of these. Okay, so in general, you can get a solution to an ODE by taking the Laplace transform of both sides of the ODE. You can rearrange to get an algebraic expression, solve for the variable that you want as an explicit for an explicit solution. You may have to perform partial fraction expansion in order to be able to get it into a form that you can find in the tables. And then you'll use the inverse Laplace to come up with a y of t for the expression from y of s. Okay, so let's go ahead and just practice on this one. Okay, here's the solution. We're going to take this one is going to become, okay, that term, and this one becomes this term, and finally here this one. Okay, so we have in this example we want to get y of s on one side of the equation. Okay, so here's our y of s right here, and then I'm going to use number 11 on table 3.1. Okay, so let's go back to number 11 on 3.1. Okay, so we found something right here. Okay, and it's just going to be that in the time domain. So we just have to figure out what our B3, B1, and B2 are, and then we have B3, B2, and B1 in the time domain as well. Okay, so here's our B3, B2, and B1. Okay, and there's our final solution. Okay, so y of t, one of the other things I'd like to do is just go ahead and differentiate this and plug it back into the original differential equation and just see if I get the correct solution. Okay, so you can differentiate that, plug it back in here, and then plug back in y, and then see if that solves, if that the left-hand side is equal to the right-hand side for your original differential equation. Okay, so we checked the answer, and it turned out to work. Okay, so partial fraction expansions. I just want to review this briefly. So if you have two roots in the denominator, we're going to need to have two alpha values or constants here. Okay, and then what you can do is multiply through the denominator and then plug in s equals -1. And if you do that, then all you're going to have is alpha 1 equals something. And then if you plug in -4, then you'll just have alpha 2 equals something. Okay, so you can determine your coefficients alpha 1 and alpha 2. Okay, and here we go, alpha 1 equals 4/3 and alpha 2 equals -1/3. Okay, so here's just a general expression for the partial fraction expansion, and d of s is called the characteristic polynomial. We're going to visit that a little bit more later, but this is going to be called the characteristic polynomial for some of our analysis that we're going to do later on in this class. Okay, you can also have complex roots. Okay, so where j is the square root of -1. Okay, and that often occurs when you have sine or cosine functions. Okay, and you could also have repeated roots as well. Okay, so anyway, so just check out these pages if you want more information on some of these special cases or more difficult situations. Okay, so we have this partial fraction expansion, and so we've created a single term for each of these denominator values, and let's go ahead and just go through this one. Okay, we get alpha 1 is going to be equal to 3, alpha 2 is going to be equal to 4, and alpha 3 is 5. Okay, and then that turns out to be this form, and then this can go back to the time domain. Okay, so we can find each of these in our Laplace tables and go back, whereas we did not find that most likely in our Laplace tables. So the reason why we have to do a partial fraction expansion is so that we can find it in our tables and take it back into the time domain. Okay, so there's our f of t for back in the time domain. Okay, so repeat factors. That's another thing to just keep in mind. If you have s plus 3 squared, you want to have a term for both of these. Okay, so you have s plus 3 to the first power, s plus 3 to the second power. If you have 3, then you're also going to have s plus 3 to the third power. Okay, so how do you get alpha 1 and alpha 2? You want to multiply this out and match like terms. So you want to collect all the s squared terms, all of the s terms, and all of the ones that are not multiplied by s. And okay, so I'm going to multiply it out, and okay, so here are all of my s terms. You'll see that there's a 1 in front of it, therefore alpha 1 equals 1. Okay, and then we also have that, let's see, equals 1. Okay, and therefore alpha 2 equals -2. Okay, so we were able to solve it with repeat factors. You may need to collect like terms. And there's our time domain solution. Okay, so one other thing to note, this is the final value theorem. that we can determine a steady state value if we multiply by s and then take the limit as s goes to 0. Okay, and that will give us the final value. So as you go to s0, you're going to go t goes to infinity, and so you don't necessarily need to transform that into the time domain to figure out what the function's eventually going to go to. And conversely, we can also do this for the initial value theorem. Okay, but this is s goes to infinity, so it's kind of the backwards. Okay, so this is initial value for that function, but that's t goes to 0, and what you do is you plug in s is infinity, and in this case, t goes to infinity, you plug in s equals 0. Now don't forget to multiply by s in the first place. Okay, the last one that I want to cover is the time delay. So this is a really important one. If you do have some time delay, you have this step function that I talked about earlier, but in the Laplace domain, it's just e to the negative s t naught. And we also use theta p in our process first order plus dead time model. Okay, so more practice. Write Laplace of a function that does the doublet test, and then changing at t equals 0 to a value of 2. Okay, so that's going to go up to a value of 2. Changing to a value of negative 2 at 3 minutes. It's going to go to negative 2, t equals 3 minutes. And then change to a value of 0 at 6 minutes. Okay, so that's 0, and that was 6 minutes. Okay, so let's go ahead and see if we can figure out how to write this in the Laplace domain. Now, this is just a step function. Okay, so I'm going to add up a couple. Here's my first step, and that was plus 2. Okay, so that's just going to be 2 over s. And then at this time, time equals 3 minutes, I had a negative 4 step. So that was negative 4. And so I'm going to write that negative 4 over s, e to the negative 3s. Okay, and then I had a final step back up by 2, but that was at 6 minutes. So I'll do plus 2, and so that's going to be 2 over s, e to the negative 6s. Okay, so if I just add all of those together, I'm going to have 2 over s minus 4 over s, e to the minus 3s, plus 2 over s, e to the minus 6s. Okay, so that might be our input function. And then, let's say we had y over u was going to be kp over tau p s plus 1. Now I know what u is, and so I could say y of s equals kp over tau p s plus 1 times u of s, plug in that value, and then convert it back to the time domain and figure out what this signal is going to do. Okay, so let's say it's going to do something like this. Okay, so we'd be able to calculate what that response would actually do. Okay, so let's go ahead and write the time domain form of the following Laplace transfer function and sketch it. Okay, so here it is. It's just a triangle. Okay, so kind of like a sawtooth function, and here is the time domain solution of that. So we can also go back to the time domain with this. Okay, let's determine the final value of the following function. Okay, so remember the final value theorem, we multiply by s, and have s goes to 0. Okay, and so I'm going to multiply by s, plug in s of 0, and then that's going to be equal to 3. Okay, so eventually that function will go to 3. Okay, so just a little bit of extra. Here's another ODE. We're going to convert it to the Laplace domain. We'll rearrange, solve for y. Again, that's why we do, a lot of the reason why we do a Laplace transform is to get it into algebraic form. And then we do an inverse Laplace, and then come up with our time domain solution. Okay, so it allows us to solve this differential equation, with different initial conditions in the time domain. Okay, and here's a partial fraction expansion. Okay, so I want to be able to convert this back into the time domain. I want to do an inverse Laplace, but let's say I couldn't find this in the tables. Okay, so I've got to break it down into more elementary pieces with partial fraction expansion. And there I go. I've broken it down into partial fraction expansion. And then when I take the inverse Laplace, I can find all of those terms in my tables. And then there's the final solution. Okay, so here's a higher order derivatives. Okay, so this is the third derivative, second derivative, first derivative of that expression. Again, convert it to the Laplace domain, and then factor the denominator, and then do partial fraction expansion. Okay, and then I can get my final solution in the time domain. So I'm just kind of going through these at a very high level just to show the main idea, which is take the differential equation, convert it into the Laplace domain, rearrange it, and then get a time domain solution. Okay, so here are a couple important properties of Laplace transforms. You can find the steady state value, and as I mentioned, this is the final value theorem. Okay, so the limit as t goes to infinity is going to be if you multiply by s and have s goes to 0, and providing that the limit exists. Okay, so if the limit does not exist, then this final value theorem, we can't actually apply it. Okay, so it can give you a false answer. So that's just one thing to consider with this final value theorem. You got to make sure that a limit will exist first before you can find the value that it will go to. Okay, so just one last example. We multiply by s and then get our final value. Okay, and that. I'll go ahead and conclude here with this Laplace transform exercise and discussion.